everyone to our very first in the Maryland Robotics Center Symposium Series of 2025. Yay! Those online, you can't hear. People are cheering and celebrating. All right, so today we have a talk that I mean, obviously, I think for those of you who know my research, I'm personally very excited for. So we have Professor Markus Nemitz, who is an assistant professor of mechanical engineering at Tufts University. And there he leads the Nemitz Robotics group. So he earned his Ph.D. from the University of Edinburgh. Am I saying that right?
Yeah, kind of.
Nope. All right. So, how do you
so Scottish people would say Edinburgh, but you can also say Edinburgh.
All right. I'm gonna go with Edinburgh. And so, so he got his PhD there in 2018, and then moved to Harvard as a postdoc until 2020. He then joined the Robotics Engineering Department at WPI. He received the NSF Career Award for his work on 3D printable robots in 2023. And so let's all give him a round of applause and thank you for coming here.
Thank you so much for having me, and I'm really excited to explain a little bit more about the research that I do in swarm robotics. How many of you are actually mechanical engineers? Aerospace? Computer science? Nice. Electrical engineering? All right. So we have kind of like a broad group of people here. That's great. So what I've been doing is studying a bunch of different topics. So I started in Germany, did my bachelor degree in electrical engineering. I got really excited about electronics. And then I moved forward with a PhD in swarm robotics, where I was, as you will see, very quickly very disappointed in the field. And then I went to Harvard, did soft robotics with George Whitesides, and then I moved from there to WPI, became a robotics faculty for 4 years, taught lots of courses in perception control, my own printable robotics course, soft robotics as well, and then now since July 2024, I am at Tufts, a faculty mechanical engineering. When I start talks, typically I do some selfish advertisement first, and so this is like a workshop that I part in organizing, which is going to be at the International Conference at Soft Robotics. And this is going to be about soft robots in really outside the lab and in real environments where they can do good. And so with a bunch of people, we really focused on who are the practitioners in soft robotics who actually bring their robots that typically live in the lab outside in the world and do something good. And so if anyone goes to a soft robotics conference, this is definitely a workshop that I would like you to attend, and then please reach out as well. Now this here is a movie trailer, and so I would like to show you a movie, and at the end I would show you how, what my part was in there.
Welcome to the first robotics worldwide competition, Afghanistan.
The computers come today for the boys.
Girls, outside.
The first time I touched a computer, it's like a light in the darkness. And my tiny world got bigger and bigger. We have no computer classes. I'll learn how to use these and then I'll teach girls in Afghanistan. 10 classrooms are a drop in the ocean. It's not changing anything. We are looking for 4 girls who would like to learn about robotics and compete with teams from other countries. It'll show Afghan girls in a new light. Are you interested in joining our team?
You're the robot lady.
How fast do these robots go?
You get to drive them in America.
It's dangerous to talk about girls doing this.
It's dangerous not to.
My answer today and tomorrow will always be no.
How did you convince your uncle?
I said if we won, I would attract a rich husband.
Of course. Every move that the robot does, it comes from your code.
We can't embarrass our country.
We have to show we can win. That bombing was sent to Tara's father from the Taliban. She has to quit the team. Doesn't matter what we do or accomplish. We come back here, everything is exactly the same. I really thought that I could change things.
If the Taliban is mad at you, that means you have. You're just not finished.
There's only one flight left tonight. If we miss it, we're dead.
This event is the most important robotic competition in the world!
This is our chance.
We have to fight. And this is how we do it. We have made a mine detection robot.
Nothing ever happened unless someone dreamed it first.
What do you want? To win.
Well,
So, that is a movie that has something to do with when I was at WPI faculty. The director of that movie, Bill Gutentag, reached out to us because he saw a YouTube video where one of our demining robots was featured. And he said, I want that robot for the movie. And then I said, unfortunately, that robot doesn't exist anymore. So he said, well, thank you, but it was worth reaching out. And then I said, wait a second, what do you actually want? Well, we need this demining robot. And I said, can you give me the movie script? He said, yeah, here it is. So I read the movie script. I, changed some technical details that they probably didn't get right. But more importantly, it was very clear that these girls who were not allowed to learn about computer science were, building these robot systems. And the person who was supporting this project was the person who actually was in Afghanistan doing that, Roya Mahbub, who now lives in New York City and had a huge role to play when the Afghani government collapsed and our American troops pulled out. And so they got many, many more girls out because of her. But this is based on a true story. And when they reached out to us, I said, why don't we build you a demining robot from scratch? Because it seems like if this is a robot that's being developed in Afghanistan, maybe it's not the Air Force robot for $20,000, but maybe it's something that is cheaper and simpler. And so we started to get like a little card we got from Harbor Freight, and we started to put a DC motor beneath. And you can see here how this is the robot. You have like a little moving arm on there, which is a windshield wiper that we got from a scrapyard. We have one of these metal detectors that I imagine seniors use when they go over the beach and look for metal. And so we put that on there. And then the entire robot essentially was very simple. We showed them that and they were excited about it. We built our own crate and shipped it to Budapest. And then me and a student went over there on the movie set to actually operate that robot behind the scenes. And so that was like one of the very exciting parts, definitely my career, and to see what it actually is like to be at a movie set and to operate a robot. And here you can see a video of the robot, how it actually, this is how people make movies. You will see that the actress doesn't say anything, she just moves her lips, but therefore the robot is in full action. At least we should see that. There we go. That's interesting. So, what you would see is a robot driving around on the sand, and then you would see, all the actors and actresses around, and then on here on the right side you would see Phoebe Waller-Bridge. I'm not sure whether many people know her, but she's essentially an actress who is known a little bit better. But ultimately, we developed this robot, and it was for demining, finding landmines. And this movie, this robot is the hero robot. Comes out in March in the movie theaters, and so we're very excited for people to watch it because it has a really interesting story. And me having my own daughter, learning about robotics already at this age, I definitely see how privileged we are here to learn everything that we want at an early age. So now about the actual research that I do. So I'm a disappointed swarm roboticist. That's what I tell people typically. And that's not because I'm overly negative, but when I did my PhD in swarm robotics, it became very clear that most people do swarm robotics in simulation. But that I mean is, what does it take to have not 10 robots, not 15 robots, but maybe 100 robots, maybe 1,000 robots operating? And what does it take? And the first problem is, you can't really make them because they are so expensive. Nobody would know how to pay for that, and then the experiments would be also very difficult to make. And so how do we push that swarm robotics agenda into the real world? back at that time, Michael Rubenstein from Harvard, who was a postdoc in Radical Nagpal's group, he developed this kilobot robot, which is 1,000 of these little robots over here that use slipstick locomotion and they vibrate a little bit around. And they did fascinating work and published a really important paper in Science. But again, this swarm robotic system didn't leave the lab. And so one exception that we have now in swarm robotic systems are drones, quadrupeds. And so that exception is pretty clear. We see that everywhere in the world. Chances are that many of us already own a drone to do photography, but you see it also in the Ukraine being used for military purposes. So why is that possible? Well, there's now such a big economy behind it, and the demand has so much increased over the years that you can actually purchase them at a fairly low cost. And so now drones are definitely possible to purchase and then use them in large quantities. However, my lab is interested in robots that are not just drones, but also terrestrial robots. And so the question is, how can we make increasingly intelligent robots without increasing their cost? If I have infinite amount of money, I can just spend money and get more intelligent robots. But how do we increase intelligence without increasing the cost? And so that's a question that we ask in our lab. And then on top of that, we're also interested in conventional robots and retrofitting them as robot carriers. So they take our little robots and put them at places where they can do real good. And what that actually is useful for, I would like to explain here. What we envision is that we have this kind of nested deployment scheme where you have like a rover that carries a drone, and that drone deploys then these smaller robots. And for instance, finds a landmine, detonates it. Because the robot is so low in cost, it doesn't matter. The robot will be destroyed, but it will also get rid of a landmine, saving lives. These are the robot systems that we have been working on: heavy payload drone, tracked vehicles. You can see this kind of nested deployment here in the top right, and also underwater robots in the pool. And so we use these robot systems as robot carriers. When I did my postdoc, the question that my advisor always asked, George Whiteside, was, who cares? And so, why would anyone care about me pushing swarm robotics? And my personal answer is similar to what we did in the movie with the demining robot, is to fight the entire demining of the world. And one of the issues is that with landmines, mostly people who die from that are often children, because they tap onto them, they fall into, they just detonate. And so what can we do about that? And one of the issues when you study that a little bit is that to plant a landmine costs like $30. But to get rid of one is significantly more expensive. And as long as we don't build robots that are as cheap as that $30 landmine, I think finding a robotic solution will be interesting and possibly difficult. And so there are lots of different ways of doing demining. We focus on building very low-cost robots that are deployed from helicopters, and then they ultimately go onto an area and they will crawl around, find a landmine, detonate it. And there are different ways of detonating them, of course, and so there are questions that can be answered. But what I would like to focus on now is what kind of robot systems could that do? This is me and my PhD students operating one of our robots, and we are essentially, none of the videos work here, that's interesting. So this is like essentially a robot that we use with the company QAS, and they have a proprietary sensor on it that they reached out to us, we put on our robot, and then we went to Oklahoma to find landmines under the ground and down to 1 meter. And so on this next slide, you can see, it's really not working. My laptop seems frozen. Okay, let's try this again. So we just had faculty interviews at Tufts, and this happened to 2 of our candidates. And I said, those were always Windows laptops. And now I'm standing here with my Mac, and I feel really silly. And so maybe putting a power. There we go. yeah, this is us moving around with that robot, and this is the in Oklahoma, the minefield that we're working with. And so you have like a bunch of over 120 different landmines that are all deployed at different, or at the same depth, down to 1 meter, and they're all sorts of different landmines. Some of them are Russian landmines, some of them are like made from glass, and so we were able to show with that sensor in our robot system, we can detect them essentially all. Obviously, when you're trying to detect landmines, you're not driving over them with a tracked vehicle. So in this case, we only facilitated to see whether the sensor actually works for finding these landmines. And so then Bloomberg was reporting on that, and people got really excited. And shortly after, we jumped on calls with some of the Ukrainians. Well, I'm not sure they were for the Ukrainian forces, but there were some government links. And ultimately, we talked to a bunch of Ukrainians, and they were interested in using that technology to find landmines, as they have clearly issues with that currently. So, landmines. I quite like to help with movies that deal with demining, and then also we go in the field and find them with collaborators. But I'm also working with the Department of the Army on hydrogen-powered UAVs. So why would I care about that? Well, hydrogen-powered UAVs can operate for 24 hours. And in this project, we autonomously refuel them with robot systems. And so we use robot systems to refuel them, and that allows you 24/7 operation. These UAVs are then very useful to deploy these smaller robots that we develop. And so I think with my research about all the other parts that have to be put in place in order to make demining actually a reality. We not only have to find landmines, but we also need to get the robots that can actually detonate them in place. And so I'm working on these things in parallel with a few companies and military collaborators. Now, today I would like to now talk about the swarm robots that we're developing, and I would like to introduce 2 different types. One of them is going to be a 3D printable lagged robot, and the other one is going to be a fluidic robot. And with the fluidic one, you will see that my main point is that while I can't 3D print electronics, I can 3D print fluidics. And that means whatever the fluidic robot does is at the cost of a spool of filament. And that's exciting to us. But let's first focus on the 3D printable lagged robot. So as you can see here, there are a bunch of examples of different soft-lagged robots, and Ryan has a really nice robot over there that he developed, and it is a fluidically powered robot that moves its limbs, and it's very exciting, and there is a bunch of other work that does similarly exciting work. Some of these robots, they incorporate some material controllers, and we now develop one of them that is also a soft robot, but we call it more soft hybrid because it's a combination of soft materials and hard materials. And one of the things that we really like is that it gets outside of the lab. So this is the robot, how it climbs up a little slope. And what we did there, we were kind of clever with how we think about linkage design, and how we get a classic linkage that we all know, 4 bars, for example, and translate them into something that is soft. And so the framework that we introduced, and this is a paper that was supposed to come out this week, but I guess it might come out next week, is this idea that there is a framework that we develop where we're very inspired by nature and how lagged animals move. And then once you identify a trajectory, a foot trajectory that you really like, you can take that and implement that with a mechanism design, a classic mechanism design. But you don't end there. You then translate that into the soft domain by assigning different materials to different parts of that lag. And when you do that, you develop actual robots that are soft and squishy, which makes them impact resistant. And at the same time, they are lagged robots that can actually traverse over environments, so they're kind of fast and useful. If you look at all sorts of lagged animals and which one's the fastest, which one's the slowest, all of them are in this case lagged. And if you look at them, how they move their legs, and if you look at the trajectory of the foot, you can see that that is a closed loop trajectory. And so that closed loop trajectory is actually quite important, and humans have obviously the same trajectory. We lift our foot and we move forward, and then we move further and so on. That is a feature of lagged species, including ourselves. Well, that closed loop trajectory is in direct contrast with open loop trajectories. For instance, this worm here that is trying to inch forward, and that's perfectly fine, but it doesn't have this closed loop trajectory. It's a open loop trajectory. And so closed-loop trajectories are particularly useful for fast locomotion. And so biology or nature has been a great teacher in that regard, and taking inspiration from that is useful to build robots that can traverse difficult terrain. So how do we go about this? You first find a legged animal that you really like, and you like it in a specific environment at a specific speed. So let's say you really like crabs and how they maneuver over difficult terrains. And you pick that particular animal, a crab, and then you see, well, that's a snow crab, and it moves kind of sideways. It doesn't seem to be too fast, but that's a typical locomotion gait. And then you take that and look very carefully at the trajectory. And once you identify that trajectory, you then can build a mechanism from that. As it turns out, and probably many of you know, whether you are, if you like the trajectories of horses, that's fine, but as they change between different gaits, the trajectory will look different. And so you really need to identify what is the animal and the trajectory and the gait that they use in this particular task, and then from there you try to replicate the trajectory. And there are all sorts of different trajectories of different animals. Crabs have a different trajectory than, for instance, other legged animals, and the octopus that move forward and have a really interesting helix type, how they move. And so you will be surprised what trajectories you can find there. Once you're there, you can essentially develop a mechanism. So in this case, it's a 4-bar, and those who are mechanical engineers and beyond, they're this classic, undergraduate or even high school idea where you have like this rocker coupler and a motor and then a crank, and when you move that, you get actual locomotion out of that. Now, if you look at this picture here on the left and then on the right, you can see that we did the same thing. You still have the crank, you still have the coupler, but we extended, and that's what people do in electrorobotics, you extend the coupler by an additional link in the coupler point, and that becomes the lag of your robot. And so if you then start to move it around, you can see how the 4-bar goes in a specific direction, and then the same thing can happen with your own linkage that you designed, but now with an actual lag. And then from there you can change your 4-bar and change how long all your different links are, and based on that you can get different trajectories, and then you find the one that closest resembles what you actually care for. Of course, once you have the lag trajectory that you picked, then you can do some trigonometry and develop like an analytical model for that. And then once you do that, you can then compare to actual simulation and the real-world experiment. It gets really interesting when you start to have identified or synthesized a linkage, and then you translate it into the soft domain. Because then these pin joints that you have here, now they, in our framework, become parts that are of different material softness. So this yellow material has a higher shore hardness than the green material. So the yellow material is more rigid, and the greener material is softer than the yellow material, which means then when you apply a moment, that little green joint will give in, and you get like a nice movement out of that. And we will see that in a video in the next few slides. But this is the important part. You go from a pin joint to something that is a multi-material design. Once you identified all of that and you did the multi-material conversion, you then can 3D print your robot. And then you see a multi-material printer, which is a Prusa XL. It has different print heads, and you print your thermoplastic polyurethane, in this case 2 different ones, and then you're essentially done with the robot body and with the legs. And then you can finally put motors on there and make it rotate and move the leg, and then you can compare what your finite element method would do in comparison to the real-world experiment. And you can see how the black line over here that you can see the trajectory, that's the analytical one that we developed from trigonometry. And now you have the simulated one, which is similar, fair enough, but then you have the one with the real-world experiments, and they are also similar, but they're also somewhat different. And so when you then look at the different softness of the different materials, you will see that the yellow one is made from a different material composition than the red one, for example. The yellow one in particular uses more rigid materials. So you can see here on the top right how you have different shore hardness, 85A, 95A. The higher the number, the stiffer it is. And so the yellow one has 95A75D, which is our most rigid material combination. So that means when the motor is trying to move that leg around, it experiences more resistance than the other combinations. And that is why it doesn't follow the exact perfect trajectory that you would have if it was a rigid system. Of course, then when you print different materials, you need to look at the interfaces and how well do they actually combine. And the moment you print two materials, especially with a tool changer, you deposit a material and then it solidifies, and then you come with the next tool head and print another material. So that interface becomes very important, and a really high print temperature helps to fuse those materials better together. What I would like you to take away is if you combine two different materials or two different shore hardness, the combined Young's modulus of the two is typically in between the two materials that you chose, which is kind of intuitive. What is also interesting is that if you have a very soft material and a soft material, it lies in between. If it is a very soft material and a hard material, it tends to be more on the soft side. And so whatever combination of materials you have, it will exhibit the behavior of the softer material, which makes sense. It's like the one material that gives in earlier than the rigid one. And you can see how here we did also cyclic testing to really show that these interfaces don't operate 1 or 2 times, but hundreds and thousands of times. Now, this is one of the things that is really exciting about it. Soft robots, every soft roboticist will tell you that, they're great because you can smash them. They survive physical impact. Well, this thing does it too. And it is not so soft that it is slow, but it is soft enough to withstand impact. And so what that means now for us is that I can get the advantage of soft robotics while still being in the domain of kind of semi-soft materials. And so this soft hybrid gives you the advantages of soft robotics and some of the advantages of hard, rigid robotics. And that combination we find extremely exciting. Now, once you do all the parameterization, you look at the interfaces, and you go through all of that, then ultimately you can put everything together. You make your own circuit board that that has Bluetooth, and you can remote control it. We put actually infrared transceiver on there, so you can actually communicate with it and give it remote instructions. But once you put it all together, you can now analyze how it actually behaves in the world. And so, as you can see here on that video here on the bottom right, you can see how we put like a little dot on here, and we do that for tracking. And so in one case, we track the foot trajectory, and then on the other, the centroid of the body, because we want to figure out how smooth does that thing actually locomote. And if you now take this combination where you have a nominal linkage design, and by that I mean we can change the linkage itself by making it a little bit more vertical or a little bit more wide. If we pick that design over here, and then we choose 2 different materials, in this case the most rigid one and the softest one, then you get these kinds of trajectories. And then you can actually analyze, what is the smoothest and best behavior. We also looked into how fast then, these robots can be. And you can see over there on the top right, we get 0.42 body lengths per second in this prototype. And then you can go through all the others. We can not just go through synthesis, but also different materials, and then you can compare them. The rigid material combination is the one that had the slowest velocity, and what you will see with the robot is that the moment the material combination is on the more rigid side, the motor has struggles with overcoming that resistance that it creates. And then everything becomes kind of stiff. And the softer you make it, the more natural it looks like. It almost feels like a biological system. And I will show you a video later on where you can see how the entire robot body moves. And we really get these features of soft robotics without landing in entirely soft domain. And I think there's a lot of real-world applications in there. So this is the robot that we currently have. It's fairly compact with 100 millimeters. It can move 250 meters, so 2,500 times its own body length. And with a 2,000 milliamp hour battery and the 3.7 volts, we were able to operate it for, I think, 1.5 hours. And so here you can see there how the entire robot body is just moving around. And so that is a direction that we like to see. And then we show how it moves over different terrains such as sand and rocks and other environments. And sometimes it struggles. And so in this case, the robot struggles. What's the problem? Well, it doesn't lift the leg sufficiently up. And so now it would be interesting to have to have a different trajectory, a different linkage for that design. And so now we're thinking about, can we change the lag on the go so it can change its linkage and change it in a way that then allows it to overcome different obstacles. When you now see how the robot does a point turn, you can see how everything is moving. You can see how absolutely everything, this is a point turn, the entire robot body is moving. Everything is somewhat moving around. And now, again, we're interested in doing a pause and print fabrication strategy where you print something, you pause, you put in electronics, you continue printing, and you do that all automated. Here my students drove with his BMW. I have no idea how he gets all that money, but he drives with his BMW over that robot. Of course, there's no electronics on there, but again, you can encase that. That's something that the Navy is now very interested in, encasing it entirely, throwing it from helicopters, these sorts of things. Now, that was all about this kind of lagged robots and how we can design them. The other one that I would like to highlight is now this kind of fluidic controller. And so that's a very different domain. The commonality is that they're 3D printed, and that means to us we can make them at a low cost. So the definition of a computer is a programmable, usually electronic device that can store, retrieve, and process data. But what if it's not usually electronic? Then you get a computer, and that computer that you see here is a fluidic computer. So you can process information electronically, but you can also process information via fluidic signals. You can store information via fluidic bistable mechanisms. You can develop entire state machines. You can develop combinational and sequential logic from them. You're back in Computer Engineering 101 where you realize, oh, I have all these different logic gates, I have all these different memory elements, set reset latches. What can I build from them? A question I typically get is, Markus, why would you go back to fluidic computers? Electronics is so good, and we already, like our transistor level with electronics is in the nanometer region. It's great. And the answer to that is, yes, your electronics is really good until it isn't. And that is, if there's a strong magnetic field, chances are your device, is being at least deleted, in the worst case, completely destroyed. If you have an electromagnetic pulse, that is something that can be destroyed. A lot of this research was also done during the Cold War era, where people were very afraid of the electromagnetic signals and also ionizing radiation that could happen from a nuclear attack. What would actually work if our country was attacked? And so fluidics has really compelling answers to that. Also, when you try to, for instance, measure magnetic fields, then typically electronics around the magnetic field sensor creates magnetic fields themselves. And so the sensor can pick up on that. However, with fluidic signals, you wouldn't have any of that. And so there are more and more of these examples. Spark-free environments. You want to operate in an environment where you definitely don't want to create a spark. There's spark-free electronics, but spark-free electronics is expensive. The same thing with space radiation. You can build electronics that is actually hardened against radiation. You can also build fluidic systems. And I bet when you're at Mars, you can 3D print whatever you want to based on what you experience, versus thinking about in advance on planet Earth and hoping what you have is good enough for what you will experience. And so there is this mindset of we should be able to fabricate solutions to the problems that we encounter. Now, these are all the reasons why I'm really excited about electronics. Some of them I already mentioned. Most importantly to me, while I cannot 3D print electronics, I can 3D print fluidics. And so I don't want that fluidics competes with electronics. In fact, it can't. But it has advantages that electronics doesn't have. So this is now the work of 3D printed fluidic logic gates. And you can see Ryan's work there as well with polyjet printed logic gates. And I love this work. And I think, I'm not sure I'm supposed to tell you, but I think I reviewed the paper. It was really, really great work, or still is. And so the question, though, is with all the logic gates that we have here, how do we make them in a way that is so cheap and reproducible that anyone can make them, first of all, and then also so cheap that we can scale them in large numbers? And so one of the things that we did, we developed a CMOS equivalent logic gate from flexing beam mechanisms that allows you to compute information and build computers. And this is how it works. You essentially have a device, that white device there on the side, and it can move between two different states. This here is essentially a complex, or not a complex, it's a bistable mechanism. It's a mechanism that has the ability to push down, and then when it releases the pressure from this soft actuator, so this is a soft actuator, you apply pressure, it goes down, you release the pressure, it flips back. And so that allows you to now compute information. Why do we close one tube and at the same time open it, and vice versa? Because that's considered complementary switching, and that is important for making devices that are actually power efficient. And that itself, I could give a lecture on that and why that is, but CMOS equivalent circuits, they're more power efficient than if you only squeezed one tube. If you only squeezed one tube up, open and closed, that would be less energy efficient for several reasons. One of them is if you have a tube, you put a pressure source on one side, and on the other side you have a balloon. That balloon inflates, 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 inflates. Now you squeeze that tube and the balloon stays inflated. But with fluidic logic, I want, whenever I actuate something, whenever I put a pneumatic fluidic logic signal 1 on the tube, I want it to be switched on, and when I release it, I want it to be switched off. So I want the balloon to deflate. The single tube, you don't get that. If you have now two tubes, one of them opening, the other one closing, and you connect that to a balloon, whenever you apply pressure to that actuator, it either inflates or deflates. So you're not anymore in that kind of state which is considered floating in computer engineering, where you don't know what your output pin actually is. Now, of course, when we develop these devices, we also want to understand how can we change, them in one way or the other. And probably the most interesting thing to do with this is, sure, you can, with our paper, you can figure out, I want this to switch at, 30 kilopascal. That you can do that, and you can figure out based on the parameters what to change to achieve that. The other thing that you can do is you can change the parameters in such a way that they actually become bistable. And so what you can see here with all these different parameters that you can change, such as beam thickness, which is over, where's T? Over here. That thickness of that beam, that can determine whether your device is monostable or bistable. Then the gap that you have here, W, that determines that as well. And so I think the most interesting thing that you can do with that logic gate is, with this flexing beam logic gate, is that you can design it in a way that it becomes a memory device. And that means that, similar to the pop toys, when you press it from the top and it flips down, you put your finger away and it flips back. Now the alternative is you have a membrane, you press on it, it flips down, and it stays there. And then you have to press from the other side to get it back up. The latter one is a memory device. You can store information on materials by just having a truly bistable system where the moment you actuate it, it stays that way. You have to push from the other side, then it's on the other side. Then you can store information. And that means that you can develop fluidic programs that are stored somewhere in your materials, and you can use them to execute different robot behaviors. Once you have one of these logic gates, you can make them to NOT gate, AND gates, OR gates. And the only difference between AND gate and an OR gate is where you put your tubes and apply supply pressure, atmospheric pressure, and your inputs. So as you can see here, the device is still the same. So if we did in our lab experiment, I would give you one device. And I would tell you, now please put on that actuator here, on that actuator, please put your input signal A, and then put atmospheric pressure on the top tube and supply pressure on the bottom, and then you will have a NOT gate. And then I would ask you to change it to an AND gate, and then you would just change that input-output configuration. And then once you do that, you get these logic gates. And so with a NOT gate, whenever the input is 1, the output is 0. Whenever with an AND gate, you have two inputs. When both are 1, the output is 1. Otherwise, it's 0. The exciting thing about that is, again, you're back in computer engineering, and now you can combine them in different ways. And one of the ways you can combine them is by putting them all in a circle. And so you put one NOT gate onto the next one, and then this one to the third one, and the third one to the first one. And because you have 3 of them, an odd number, there's no stable state. How could it be? You have a NOT gate that outputs a 0, that goes into the next one, that becomes a 1, the 1 goes to the next one, that becomes a 0, and then the 0 goes back to the first one, and that was previously a 1. And so there's an instability in states. And that means that if you put 3 NOT gates together, it's called a ring oscillator, you get spontaneously an oscillating signal. And so that's really exciting because it means that I can apply a constant pressure, such as from a CO2 cartridge, and then you get as output an oscillating signal. Now that is really important because that pattern generator can be used now to actuate, for instance, legs or whatever else you want to do. A swim bladder of an underwater robot, whatever you want it to be. So this is a central part of these fluidic logic systems where constant pressure in, oscillating signal out. This is now a demonstration. This is not the robot that will go on the minefields and detonate landmines, but it allows us to study fluidic systems. And here you can see how we have a ring oscillator with 3 of these NOT gates together in a circle. And then when we apply that output pressure to that robot, it inches forward. And apologies that this video again stopped. Let's see where that... No. There we go. I'm not sure. My laptop doesn't like me today. You can see how it essentially moves forward. And then you can see also here how these NOT gates, they're connected to atmosphere, but I put it along a tube here at the outside. And depending on how long the tube is, as you can see here, you can change the oscillation frequency. And so, again, there are parameters you can play with, and then depending on what oscillation frequency you pick and select, and then you get the oscillation frequency. Here we just, for fun's sake, my student surprised me with a stepper motor, which I thought was really interesting. So now you have a constant supply pressure, you get an oscillating signal, and then from the oscillating signal you get rotary motion. And so now we're in the business of rotating like motors with a constant supply pressure. And again, this is like a demo to show what we can do. Putting that in a robot will be more difficult, but it shows you the idea of what you can do with just 3D printing. I mean, we're talking about 3D printing with thermoplastics, polyurethanes. It's not an expensive printer. In fact, the printer, you can print that with the Prusa Mini, which costs like $400. Obviously, if you do multi-material printing, it gets a little bit more expensive, like maybe $3,000. But it's very inexpensive to make these systems. In fact, all of this you can actually do with a Prusa Mini, because all these materials are single materials and then they're being assembled. So it's pretty exciting. And when I teach my printable robotics class at Tufts, students, they pick up on that and they implement their own stuff. And they do make jellyfish that go up and down in a water column, or little robots that walk on the bottom of a water tank and so forth. So the cost of this fluidic stepper motor, half of it is really just materials, but it sums up to like $6 or so, $6.73. And so again, be excited about it because it is inexpensive. Back then I worked at WPI, and so we also developed a fluidic display. And so the idea being you have this kind of slit tube display. Again, you can 3D print that, where every pixel here is essentially, there's a membrane, and the membrane is either popped up or popped down, and it is colored red. If it pops up, it pushes through a slit membrane, and then you see, the red pixel. And when it pops back, the slit, can cover the entire membrane again, and then it's white. So it's just a pixel on and off, and then you can access them. And so again, computer engineering now, by having only 2 inputs, A and B, and all these different pixels, how can I write, WPI? And then you do essentially the logic, you optimize it, and then you get the minimum Boolean equation for that, and you implement that. And we even developed software that allows people to do that more intuitively, where they can go on their browser, they can say in the truth table, these are the inputs, this is the output that I want, generate me the table, how I need to connect all my logic gates, and it spits it out. And so that is something that we're very excited about, and these fluidic displays are a good demo for this sort of thing. This is how it actually looks implemented. You have 5 logic gates, and then you can switch between these different states. So here my student switches on the supply pressure. We have 2 inputs, A and B. We have 4 different pixel configurations that we want. Nothing, W, P, and I. And so he goes through all the different states, and that's how we can now show how the information is being displayed. Now, this is the conclusion of the talk. Soft mechanism design, the one that I showed you with the lag, is pretty robust and cost efficient, and I think we're getting there where we can use them for practical applications. Fluidic systems are interesting to us because they will only cost as much as a filament spool. And in the conventional trade-off in robotics, more money, more capability, we want to do more capability at absolutely no more cost. And so what I 3D print today will be in a year, in terms of design, much more sophisticated and will have much more capability, yet I spend exactly the same amount of money. And so there's a lot of design space and opportunities there. In terms of miniaturizing these devices, that is also something we have been working on. However, I always say people, that's not the goal. The goal is not to make it as small as possible because we're not competing with electronics. We can make it smaller to some extent in order to stack them. But to me right now, the next thing is how can we 3D print them on a print bed, these fluidic transistors, and connect them automatically so that you can have almost like a fluidic description language where you can define a behavior, the computer automatically determines what is actually the hardware that has to be generated, and then it puts it all out, and you just press a button, and that logic is being 3D printed together with fluidic actuators, and then the robot can walk off the print bed. A little bit further away, so my NSF career grant really helps me to double down on that. This soft robot with the leg one that you see here on the top is something that now the Navy seems to be excited about, and so we double down on that and try really to get robots that can be thrown from helicopters and then move in beach and also subsea areas. All right. And with that, I would like to thank my research group. I have 4 fantastic PhD students. I'm hiring right now a 5th one, maybe a 6th one, it depends. So the application season is a little late, but if any of you is ever interested in a PhD, please do consider Tufts in my research group. The nice thing about soft robotics is that we always integrate a lot of undergrads in our research, and that's useful for them as well because they go to really good schools for their PhDs. Then this funding that we have from the US Army is extremely helpful. The same thing with some EPA grant that we got, and then the NSF funding. And with that, I close my talk. Thank you. Any questions? I've thrown a lot at you, so let's see. Yes, please.
Hi. First of all, thank you so much. It was a wonderful talk. And in the beginning, I was wondering, you were talking about a rover and a drone, and where you drop a 3D printed robot near a landmine. So I was wondering, is there any purpose given to the 3D printed robot, such as decommissioning the landmine or something like that?
You mean, can you ask the question one more time? Do you mean, does this system already exist, or what do you mean?
So basically, we drop a 3D printed robot near the landmine. So I was wondering, what exactly does the 3D printed robot does? Does it detect the landmine, or does it help, removal of that landmine or something?
Yeah, that's a very good question. So the company that we're working with develops these really sophisticated sensor system that allows us to find landmines down to 1 meter under the ground. That sensor has to live on a sophisticated robot that keeps the sensor safe. And so the idea is that you have drones flying around and actually identifying landmines under the ground. And once you then deploy your robots, you give them instructions, go here, there, 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 and they can communicate with one another, which gives them some advantages as well. However, in a scenario where landmines are not buried underground, but they're more superficial, you can put metal detectors, for example, in them. And then the moment the robot found something that feels or detects it like metal, then it can just stay there. And then it has options what to do. You can put, for instance, a strong pressure signal into an actuator that smacks into the ground, and that can detonate the landmine. You can also put a very small shaped explosive on there, which is something that my lab will not do. But I think maybe the Navy, and if they did, they wouldn't tell me. Something that we really like is the idea of them, once it is deployed, it crawls onto a mine, and then it will unfold a structure that captures the area around it. And so soft materials are great because they can expand so much. We have been working on some metamaterials where you can 3D print essentially structure into your layers. And then when you go to shooting range and shoot at it, you can see how projectiles are slowing down based on how you design it. And so we have a lot of impact on material choice, but also design. And so the idea being that these small cost robots, they go on the mine, they unfold this umbrella, detonate the landmine, then the shrapnel that is being put into all directions is being absorbed sufficiently by that robot so that it doesn't actually hit the drone or even worse, a human. So there are different strategies how to do that. Currently, we're trying to really get them now deployed by helicopters and see whether they, surviving, moving around, being useful. But it's a very good question. Yeah.
Yeah, really interesting stuff. So when you talk about swarming, I think of collective behavior, and then you mentioned you have this fluidic oscillator. There might be like a central pattern generator for an individual robot or something. Right. Have you thought at all, and I'm curious to hear if you have any ideas about how you might be able to couple multiple oscillators to achieve synchronization or some other type of collective behavior?
So essentially synchronize oscillators between different robots and get them
For example, or I mean, it could even be within a single robot if there were multiple CPGs for different gates or what have you. But yeah, just in a very abstract setting, you've got your little oscillator, now you've got 100 of them. How might you get them to synchronize through either fluidic or mechanical or optical interactions?
That's a very good question. And so what that boils down to, and I will simplify that with a pop toy, we have these robots that have many of these logic gates integrated into them. And now that oscillator powers the robot and maybe moves the legs, move around in certain ways. Something that we have proposed but haven't yet established is that if this is part of an oscillator or if this is a memory device, if this is a fluidic memory device, you can, with a low-cost microcontroller, switch membranes electronically. And so that means that you have a fluidic memory that allows for different programs to be executed. And now a microcontroller sits on top and says, now's the time to execute it. And the moment the microcontroller now writes into that fluidic memory and flips the membrane, and that can be done differently. It can be done with joule heating, for example, and there's a low boiling liquid in here. That evaporates and then it pressurizes and that membrane flips down. The moment that membrane flips down, it executes its oscillating behavior. That can be triggered with the MCU. And that means that now you can have different robots, first of all, move at the same time and getting all the oscillators exactly at the same time activated. But also if you had now, let's say, 2 different ring oscillators, you can start to synchronize them as well, and then you have essentially 2 times 3 outputs. And then you can synchronize them in a way that it allows you to operate in different gates, because now you have 6 outputs instead of just 3, and you can synchronize when they exactly start. You can also connect the oscillators with one another, and that can also synchronize them. And so there are different ways of synchronizing them within the robot and then between robots, but between robots has to be done with electronics then. And these really low power, inexpensive electronic interfaces that are able to write into fluidic memory something that we would like to develop. And we have a few ideas, and one of them was like a diode, essentially. It's essentially a blocked fluidic tube, and when you apply a current through a conductive piece within it, it essentially burns through, and then air is being released through the tube, and then you can actually, write into memory. But there are probably different ways of doing it.
Yeah, that all sounds plausible. I'm wondering, I don't know if you've ever seen, there's a nice YouTube video, if you put a bunch of metronomes on kind of a rolling platform, they eventually do synchronize just through the physical interactions. Yeah. Might be interesting to have some kind of similar demonstration without additional circuitry or anything showing synchronization.
Yeah. So between these individual oscillators, but with some kind of environmental stimuli. Yeah, that's a pretty cool idea. Yeah. Yes, please.
Duncan, Dr. Nemitz, I really appreciate the talk. So I'm a part of Dr. Sokol's research group, and we don't actually do too much FDM printing. I wanted to know why specifically your group focuses on FDM printing as opposed to some of the other modalities.
Yeah, that's a good question. So what are the alternatives to FDM? We have stereolithography, we have selective laser sintering, which is more for metals, We have polyjet printing, which I hear you guys do quite a bit.
Used to.
No,
anymore.
No, in nano.
Well, I found out recently, actually the school got rid of our Conex. It broke.
Okay.
That was like 400. So we've shifted more to VPP and then TLW. So.
Got it. Yeah, and so there are only so many ways of doing it. Stereolithography, I'm interested in inexpensive technologies, not because we can't afford it. I mean, I just purchased a polyjet printer, and we were going to explore stuff with them. But we want to have low-cost printers because that also means that we can make our robots in an inexpensive way. And so FDM printing is inexpensive. That's very excited about it. The second reason is FDM printing allows easily for multi-material prints. Think about stereolithography. That's not commercially available. If you go to conferences, people talk about having a resin that is being activated by different wavelengths, and so then you can get some multi-material stuff. But as far as I know, that's still experimental. And so, what other opportunities do we have in terms of multi-material printing that are inexpensive? That is why we're so much focused on FDM, and now we have something that's we think is even more exciting, which we work really hard on. And now you guys can probably scoop us, but I will say it anyway. And we're doing pellet printing, and so all the filaments in the world are being made by these companies. They make filament spools. And so one asked the question, why do we print with filaments? And the answer is we print with filaments because they act like pistons and they can be pushed into the hot end and then it melts and it all works. That is good for rigid materials. The moment you have soft materials, that piston that you push in is buckling and then it buckles out of the gears and then all sorts of issues can come up with that. Of course, you can then buy upgrades that compensate for that a little bit. But why do we print pistons to begin with? And all filament manufacturer, they print, the product is a filament, and the input are pellets. They're like little, granular pellets, and then they purchase them in large quantities, in thousands of kilograms. They put them into the machine, and a filament spool comes out, and that is what we purchase. But there are way more pellets in the world than there are filament spools. And so they rob me from a vast range of materials by dictating me what I can print and what I cannot print. And they will only offer filaments that they think are commercially viable. How many people print elastomeric material to begin with? And so that is where we are now drifting towards pellet printing, conductive pellet printing, extremely inexpensive and quite reliable and much faster than FDM printing. And so, yeah, it's a good question.
Sorry, Molly. We're gonna call it. Listen, we have a good 15 minutes. All right, so we won. Let's give a round of applause to our speaker.
Oh wow!
This is a little present for you.
Thank you so much. I appreciate it.
I realize now I should have been a crab, but spoiler, it's a terrapin turtle. It's our mascot.
That's awesome.
But thank you so much. That was an awesome talk. I believe my group is going to have a ton of questions for you. So we have until 3:15 if you want to hang around and people want to come up and ask questions directly. But we only pay them for the hour, the people who are recording this. So we're going to call it for this part. Thank you so much for everyone for coming. I hope you really enjoyed the talk. I obviously personally did. But everyone else, thank you again. Hopefully see you in a couple weeks. We have our next speaker. I think it actually might be next week. But otherwise, see you all soon. Have a great weekend.
Thank you.
Yeah.
It's a turtle.